Welcome to the 9th Annual Oak Ridge Postdoctoral Association Research Symposium poster session. I am Zhi-Yuan, a postdoctoral research fellow from Vanderbilt University working on genomic privacy in the Health Information Privacy Lab. If you are interested in this topic, you're more than welcome to go through my poster, download it. I'll stay here for about 6 minutes and allow me to give you a more detailed introduction. If you have any questions, feel free to contact me through email. I really appreciate your interest and time. Now let us get started. I'm going to skip this abstract and start from the background. One of the most important reasons why genomic data should be shared is that it is beneficial to the whole society. First of all, genetic testing can help the doctors and patients with the diagnosis of diseases, especially those can be treated, and the establishment of more effective drug regimens. The genetic testing was brought into the public spotlight by Angelina Jolie about 8 years ago. Second, sharing genomic data can help discover new associations between disease and genes, especially for rare diseases. Last, to help enhance transparency, reproducibility, and for reuse of data for novel investigations. Genomic data from NIH-funded studies are expected to be shared to dbGaP and to be de-identified. As anticipated, more and more genomic data were being collected and shared during the last 2 decades. We are now in a big genomic data era. One reason is that the cost of genomic sequencing keeps decreasing, much faster than Moore's law. About 2 decades ago, it cost more than $100 million to sequence a whole genome. 1 decade ago, it cost $10 million, and now it costs less than $1,000. Correspondingly, started at the beginning of the 21st century, the International HealthMap project has only several hundreds of subjects. About a decade ago, the International 1,000 Genome Project started to collect genomic data from several thousands of individuals, whereas recently, the All of Us research program aimed to collect genomic and medical data from 1 million individuals. Sharing individual-level genomic data is useful but risky. Sharing added frequencies about the pooled genomes is still useful but also risky. In 2008, Homer introduced an attack. To facilitate the attack, the attacker needs to know the genome of the target Y. The allele frequencies of the mixture or pool of genomes he is attacking M, and allele frequencies of a reference population POP, that is a public knowledge. For each SNP, there are basically 3 cases that can happen. In the first case, the allele frequencies of the target is closer to the one of the mixture than to the one of the population. A distance measure is calculated to be a positive value, thus it suggests that the target is more likely to be in the mixture. In the second case, the distance measure is 0, and it suggests that the target is equally likely to be in the mixture than in the population. In the third case, the distance measure is negative, and it suggests that the target is more likely in the reference population. As a result, NIH removed summary statistics including allele frequencies from dbGaP. In addition, more powerful attacks came after Homer's attack. Technical countermeasures include SNP suppression, noise addition, etc. Legal deterrents include data use agreement and penalty. Most of previous risk assessments assumed a worst-case scenario where the attacker has unlimited means and resources. The decisions people are making are based on what is possible and what is probable. In our adversarial model, the attacker is driven by economic incentives. He or she only attacks when it is profitable. With an accurate risk assessment, a portion of the data can be shared in an acceptable risk level. Take a step further, our goal is to mitigate the risk combining both technical and legal deterrents and to find the ideal balance between the utility and privacy. To solve this problem, we assume the data share is also driven by economic incentives. Specifically, we model the genomic data sharing process as a one-shot stack-over or leader-follower game between the data share and the data recipient. Next, we're going to show a scenario where the game would be played. We have a share, we have a recipient. The share will decide which region of the genome to reveal and how much to penalize the recipient in the event of a privacy breach. For each target, the recipient has to decide whether or not to run an attack. There is a cost associated with each attack. When the prediction is correct, the recipient receives a payment, and the share loses money due to a privacy breach. In the game, for each sharing strategy from the share, the recipient would find the best attacking strategy that maximizes his or her payoff, which is the difference between his or her benefit and costs, the cost of penalty and the cost of access. After simulating the attacker's optimal choices, the data share will choose the best sharing strategy that maximizes his or her payoff. Note that his or her benefit is dependent upon the valuation of the released summary genomic data. The biggest challenge of solving this game is that the strategy space is extremely large. The size of the strategy space increases exponentially as the size of the dataset increases. Due to the high dimensionality of the genomic dataset, searching the entire strategy space for the optimal strategy becomes almost impossible. We used a genetic algorithm to search the space. However, better heuristics can be used as well. We use data of the Sphinx project from the eMERGE network, an NIH consortium that wants to share genomic summary statistics from patients to the public. This was what their website looked like. We also use data from 1,000 Genomes project, and we assume only statistically independent SNPs from a total of about 51,000 SNPs are going to be published. Here's the valuation we set up in the experiments. Here come the experimental results. The vertical axis represents the proportion of the successfully detected individuals in the pool. The horizontal axis represents the utility metric, which is the proportion of released SNPs. Here's the ideal policy that has perfect privacy and utility. It cannot be reached just for orientation. Payoff is a way we combine privacy and utility to give an ordering of the policy. It can be a linear function of privacy and utility metrics, and more specifically, utility plus privacy minus 1. This is a result when summary data is released resulting in protection. These are results of different policies for SNP suppression approaches. This is operating point of the existing SNP suppression policy. This is a result if you change the valuation of the data by penalizing the attacker for violating the contract or data use agreement. This is where our game theoretic policy ends. You can see that it traces some utility for privacy comparing to the data use agreement policy. Most importantly, it has higher payoff than all the other policies. We can also add constraints on the privacy level. For example, we can reach the highest privacy level and still obtain a payoff that is larger than the existing SNP suppression policy. We also did a series of sensitivity analysis on most key parameters in the model. For example, this sensitivity analysis on penalty showed that no matter how the penalty changes, our game theoretic policy outperforms all the other policies in terms of monetary payoff. The trends are similar for the sensitivity analysis on probability. Some not key findings including the game theoretical solution achieves the highest payoff for the data share. No tech variation of the game can achieve a payoff higher than the state-of-the-art SNP suppression strategy while eliminating privacy risk. The game theoretical solution is not sensitive to change of key parameters such as the penalty and the probability. Some of the future directions include more accurate valuation model, multiple adversaries in the game model, and the consideration of the irrational adversary. That's all for my postdoctoral presentation. Thanks for your patience.